Thank you, Andrew. Thank you, Andrew.
You're welcome.
I mean, literally speaking, sometimes when you're doing these meetings, you have no idea who's seeing what.
Yep.
So thank you very much. How things going for you?
Good. Actually, last Thursday, right before class, or a few hours before, I actually had a job interview.
Good for you.
Starting next month, I'll be working for Sunstar.
Fantastic, Andrew. You know, you got to enjoy these little triumphs.
Yep.
Really, truly, because there's going to be enough downtimes in life that you are going to have to overcome them. Okay.
Yeah. It just
But that's fantastic. What will you be doing?
I'll be working as an EMT.
Good. Great. So I used to have a girlfriend that was an EMT in Fort Lauderdale for the longest time. And what she did was she went back and got her nursing degree and eventually got her PhD in nursing. So anybody like my dog?
It's everything is black.
Yeah, everything's black. Yeah, sorry. That's part of the problem of where I'm at right now. And that's going to change soon, guys. I got my pathology report back and I'm good to go. Woohoo!
Woohoo! Congratulations.
Thank you. Thank you very much. Has anybody looked at this lab tonight?
A little bit.
A little bit.
Yeah, I read over it.
Confused as hell?
A little bit.
I'm sure you are. I know my people have had the gas laws. Have you guys had the gas laws? People that don't have me in lecture. Have you had the gas laws yet?
We covered it briefly yesterday.
You're going to be going into more depth?
I hope so.
Is that a Heart album?
It is, yeah.
Okay. You are far too young. Heart was playing when I was in my sophomore, junior year in college.
They're one of my favorite bands. Best bands I've seen live.
That's part of that old Seattle scene, I guess. I got 10 of you here. That's about half, so I guess that's about, hopefully the rest of you will be looking on here. Let's see, who else is out there? Alec, you doing okay?
Oh, yes, sir.
Nathaniel, you doing all right?
Absolutely.
Sheridan? Got to hear from you, Sheridan.
I'm doing good.
Absolutely great, guys. We're going to get through this. There's a lot of crap going on in this experiment. It is a great experiment because it gives you a visual for limiting reagent. Literally speaking, what happens in this overall of this experiment is that you're creating carbon dioxide gas and you're collecting it in a balloon. Now, the balloon's going to continue to get bigger until your limiting reagent changes. Now, you're changing the amount of the sodium carbonate you put in there, but your acetic acid stays the same. So eventually, as you keep on adding more and more sodium carbonate, you're going to eventually exceed the amount of acetic acid you have. When that happens, you switch it from being the sodium carbonate being the limiting reagent to the acetic acid. So what happens is the balloons continue to get bigger and bigger until they reach that point. So it's good in that aspect. It gives you a visual as to saying, hey, these things aren't getting any bigger. Why not? Well, it's because you've switched over the limiting reagent. However, it has its own problems. One of which is, have you ever seen a balloon that's totally spherical? Generally speaking, balloons, come on, this is St. Pete College. We're not getting the real fancy balloons. We're going out to Walgreens and getting a bag, plastic bag full of balloons, right? Are they going to be the good balloons? Are they
No.
going to be this nice sphere?
No.
No.
So as a consequence, when you're trying to measure the volume of the balloon using the formula of a sphere, you get these crazy things and you have no idea which side to put your calipers on. So in a way, it's better that we're doing it this particular way. Okay, so where did it go? Hold on a second. I got to go grab the PowerPoint. I swear it was here. Apparently not. Okay, sorry. This is what happens when you have too much time. You get to get on ESPN and you get in one of those picture things that you keep on going through. No, this is not where I want to be. That's where I want to be. Thank you. Okay, so we'll get through this as quick as possible. You guys realize that this is our next to last lab. I know you're all sad about that. Okay, why can't I get people in? I have 14 people in here. There it is. Okay, so this particular experiment is called the balloon races because basically what you do is you fill 5 balloons up. You put sodium carbonate in 5 balloons. You fill 5 flasks with acetic acid. And you take the balloons, attach them on top of the flask, flip them over, and the bubbles come up. And they make the carbon dioxide, which fills the balloons. All right, let's go back to stoichiometry, because that's basically what we're dealing with in this experiment. 3-step process. Turn your known into moles. You guys now have 4 ways of getting moles. Grams. Sorry, I have to see these people. Why? I can't understand. Oh, there we go. Sorry. There are 4 ways you guys have of making moles. If you have grams, divide by the molecular weight. If you have liters of a gas at STP, multiply the liters by 1 mole over 22.415. If you have concentration in volume, turn your volume into liters, multiply it by the concentration. And now you have a last way, the ideal gas law. PV is equal to nRT, N being moles. If you want to find moles, take your pressure of your gas times your volume of your gas, divide by R, which is a constant, times the temperature of your gas, and you will get it. So, stoichiometry, first step, you got to get moles of what they give you. Then you look at the formula, you look at the chemical equation. You find out how many moles of your unknown you make for how many moles of your known you have. Easy enough, guys. All you got to do, the stuff you want to turn it into, that the coefficient in front of that chemical goes on top. The coefficient in front of your known chemical goes on the bottom. Last step. The question's going to ask you to do something with the moles of your unknown. You just have to be able to do it. It's really a 3-step process. If you want grams of your unknown, you got to multiply it by the molecular weight. If you want concentration, then what happens is you just got moles. The question will give you a milliliters of your solution. Divide the moles by the milliliters, and you got your final answer. Okay. In the PowerPoint, I have all your choices. Step 1 of the stoichiometry. There are 4 ways you have of making moles. These are the answers. Step 2, if you've got a molar ratio, that is a way of turning moles of something new from something old. If I have moles of NaCl and I want moles of PbCl4, the coefficient in front of the PbCl4 is 1. The one in front of the NaCl is 4. I put the 1 over the 4. Now, this is the one where it gets a little complicated. There, as best I can figure, there are 7 things that the question can ask you. And this gives a synopsis of how to go through each one of the 7. Do I have any questions on stoichiometry? Do you fairly have a good background in stoichiometry? Allie? You feel good about it?
I do.
Neela, you feeling good?
Yes.
Are you feeling good about stoichiometry?
Yes, I am.
Good. Nathaniel, we good about this?
Absolutely.
All right. Now, we're going to go through a couple problems just because I want to. You got 40 grams of NaCl. It's added to an excess of lead nitrate in 40 milliliters. What is the final concentration of your lead chloride? Andrew, how are we going to work this?
So turn the known into moles.
Turn the known into moles.
So the 40 grams of, yep, fat.
That, okay. We're just going to multiply your grams by 1 mole over the molecular weight of sodium chloride. All right, Neela, what do I do next? Neela,
Yes, I am here.
all right. I've got moles of NaCl. Now, what do I want? If I eventually want the concentration,
Oh, you take the moles and put it over liters. But first
Okay.
you have to turn 40 milliliters.
but what is this? You were right for the 3rd step, but what is this moles of?
NaCl.
So what's the next step that I have to do? I want the concentration of what?
Oh, PbCl.
So what do I do now?
You need to find moles of PbCl.
How do I do that?
You take the moles of
I can play this game too. You have answers, I have questions.
you have to take the moles of the NaCl and multiply it by the moles of NaCl on the bottom, 1 mole of NaCl on the bottom, and then you have 1 mole of PbCl4 on the top, and then
Neela, what's the number in front of the NaCl?
4.
So is it 1 over 1?
It's 1 over 4.
1 over 4. There we go. I got 0.177 moles. Now, Neela, what do I do?
Now you take the 40.0 milliliters, turn it into liters, and then put moles over liter.
So overall, I do this problem. My concentration of my lead chloride is 4.278 molar. Guys, isn't it? Think about this. Think about how much knowledge you guys have gained over the last 3 months. Would you have been able to do anything near this in January?
No.
I think it's great. I think it's absolutely fine, fantastic, because you know what's happening here? I'm not even getting hesitation. People are knowing what to do, which makes me feel great. All right. Now, there's also something called a limiting reagent problem, and it's a special kind of stoichiometry. The way you recognize it, you're given a way to make moles of two different reactants. What's going to happen is one of the reactants will run out. So what you do is you figure out how much product both of them will make. Then once you do that, you determine which one's smaller. Then once you determine which one is smaller, that's the one that produces that amount of the product. I mix 75.82 grams of sodium chloride with 147 grams of lead nitrate. How many grams of lead chloride can I make? First step is what? Armethea. Armethea, how you doing?
Hi.
What's the first step? I have 75.82 grams of sodium chloride and I have 147 grams of lead nitrate. What's the first thing I do in stoichiometry all the time?
Turn into moles.
Turn it into moles. I've got grams, so I'm going to divide by the molecular weight. In the case of sodium chloride, that's 58.55. In the case of lead nitrate, that's 455.24. I have 1.30 and 0.323. Now, can I determine from this step what the limiting reagent is?
Yes.
Am I shaking my head enough, Armethea? No. You have to take it through the molar ratio step. Have to. Okay? So, Armethea,
Yes.
if I have sodium chloride,
Yeah.
what is the molar ratio between lead chloride and sodium chloride?
1/4.
1:4. What is it for lead nitrate and lead chloride?
1:1.
1:1. So I'm going to take my sodium chloride, multiply it by 1/4. This gives me 0.325 moles of lead chloride. I'm going to do the same thing for my lead nitrate. This gives me 0.323 moles. A lot closer, right, Armethea?
Yes.
So which one's my limiting reagent?
The lead chloride.
Lead chloride, perfect. Now, the question asked me, how many grams of lead chloride do I have? If I've got moles of lead chloride, what do I do now?
Turn into grams. Yeah.
How am I going to turn it into grams?
Avogadro's number.
No. Avogadro's number gives you molecules.
Oh.
What gives you grams?
I don't know.
I don't know. It's a great response. Marie, do we know? Do you know, Marie?
I can try.
All right, I have 0.323 moles of lead chloride. How many grams? How do I determine how many grams of lead chloride I have?
Divided by the molar weight of lead chloride.
Okay, if I divide by the molar weight, that means I've got 1 mole over grams. So I've got
Okay,
0.3 times.
time 1 mole divided by molar weight.
No. Times the molar weight over 1 mole.
Oh yeah, we're looking for gram. Yes.
We're looking for grams. So the molecular mass is 349 grams per mole. Looky here, Marie. If I have grams per mole, moles cancel. All
Yeah.
that's left is grams.
Yes.
Okay?
Mhm.
You put 4.04 grams of aluminum in 300 milliliters of 1.25 molar HCl. How many liters of H2 do you generate if the pressure is 840 torr at 25 degrees Celsius? Oh my God. First thing I got to realize, I have a way of making moles of aluminum and I have a way of making moles of HCl. So first off, it's a limiting reagent problem. Then it's asking me for liters of H2, but the pressure and temperature aren't standard. So that means I got to use something called the ideal gas law. So Candace, who's Candace?
That's me.
All right. So is it Julie?
Huh?
Oh no, who are you?
I'm Donovan.
Donovan. Sorry, Donovan. Donovan,
Yeah.
how am I going to make moles of my aluminum?
I don't know.
I don't know is a perfectly good answer. Jordan,
Yeah.
how do I make moles of aluminum if I have grams?
Divide by the molar mass.
Divide by the molar mass. Okay. So I'm going to do that for aluminum. Sheridan,
Yeah.
I've got 300 milliliters of 1.25 molar HCl. Can you tell me how I'm going to get moles of HCl?
You have to, we'll turn the milliliters into liters and then multiply it by the molarity.
Absolutely. So we're going to do that for both of those things. I got 0.150 moles of aluminum after I divide the 4.04 by the molecular weight. I've got 0.375 moles of HCl. Can I look at this right here and determine what the limiting reagent is? Crickets. Look, I've got moles of aluminum and I got moles of HCl. Can you tell me right now what the limiting reagent is?
No.
No, you can't. You can only tell the limiting reagent after the mole ratio step. So I got to see who else. See who else is here. Kaylin. Hi,
Hello.
Kaylin. If I have 0.150 moles of aluminum,
Mm-hmm.
I'm trying to get eventually to H2.
Yeah.
All right.
So,
I have a pressure and a temperature. I want liters. If I have a pressure and a temperature, this is 3 of the 4 properties
for the ideal gas law.
for the ideal gas law. So if I have 0.150 moles of aluminum, it'd be a real good idea if I can make hydrogen out of that, right?
Yes.
What's my molar ratio?
3/2.
3/2. How about my HCl?
6/2. Oh, sorry, 3/6.
3/6. So I'm going to take my moles. I'm going to multiply my aluminum by 3/2. This gives me 0.225. I'm going to take my moles of HCl and multiply it by 3/6. This gives me 0.118. Please, quickly, somebody, what's my limiting reagent?
HCl.
And how many moles of H2 have I made?
0.118.
Now, I have moles of H2. I have a pressure and I have a temperature. All I have to do is convert my pressure to atmospheres, convert my Celsius to Kelvin, and insert it into the ideal gas law. Okay. It gives us 25 degrees. I add 273 to it. That makes 298K. I have 840 torr. I multiply that by 1 atmosphere over 760. This gives me 1.11 atmospheres. Now, I want the volume. For those of you that haven't been exposed or have not been exposed to this to a great degree, it's not all that uncommon because this is right at the point when we're teaching the ideal gas law. The ideal gas law says pressure times volume of a gas is equal to the number of moles of that gas times R, which is a constant, times the temperature. If I use the constant as 0.08206, that means my label is liter atmosphere per degree Kelvin mole. What that means to you is that the pressure has to be in atmospheres, the volume has to be in liters, and the temperature has to be in Kelvin. So a PV equals nRT. My volume is equal to my N, my moles, my 0.188, times my constant, times my temperature in Kelvin, divided by my atmospheres. I do this math out, and we get 615 liters. So guys, that's just a couple examples of what we can do with stoichiometry. Now, let's get into what we're dealing with the experiment. As I said earlier, we're adding different masses. We're increasing the amount. For each trial we're doing today, we are increasing the masses of the sodium carbonate. But what we're doing is we're adding it to the same volume and same concentration as the acetic acid. Moles of acetic acid doesn't increase from one trial to the other. The moles of the sodium carbonate do because we're adding more mass of each one. There's going to be a place where the limiting reagent will cross over from the sodium carbonate to then being the acetic acid. This is the equation we're doing. One sodium carbonate reacts with 2 acetic acids to make 2 sodium acetates, 1 water and 1 carbon dioxide. We're producing carbon dioxide. Now, according to Avogadro's law, it says the more moles, the bigger volume. So as long as the moles of the limiting reagent keeps on increasing, the balloons should continue to get bigger. Are you buying that logic? But remember, we have the same amount of acid. So when we switch over, we're not putting any more moles of CO2 in there because we're limited by the acetic acid. Am I saying things that make sense here, guys? All right. So we're going to use our grams of sodium carbonate to find out how much CO2 that can make. We're going to use our molarity and our milliliters of our acetic acid to determine how much CO2 I can make. We know that right off the bat. Each example, we're putting 100 milliliters times 1 liter over 1,000 milliliters. That's 0.100 liters of acetic acid times 1 mole per liter. This makes 0.100 moles of acetic acid. And my limiting ratio is 1 to 2. So each time we're putting acetic acid into one of those flasks, we're putting 0.05 moles of CO2 out. So we're going to compare. We're going to find our grams of sodium carbonate, find out how many moles that is. That's a 1-to-1 relationship. And we're going to compare the moles of the CO2 made from CO3 to the 0.050 made from the acetic acid. Remember, the smaller one is going to be the limiting reagent. Now, we're going to compare. What we've done to this point is we've determined the moles of CO2 we should make. Anytime you're doing stoichiometry, that's the amount you should be making. So we're going to use the moles of CO2 predicted by the limiting reagent. We're going to use the ideal gas law to predict how much volume we should get. We're going to compare that to an actual measured amount. So, our practice problem. We got 1.75 grams sample of sodium carbonate. It was added to 100 milliliters of 1 molar acetic acid. Predict the moles of CO2 produced using this number, and we are going to use 298 room temperature as our K. And since we're near sea level, we're going to use 1 atmosphere as our pressure. I predict from 1.75, I multiply that by 1 over the molecular weight of sodium carbonate. I get 0.0164 moles of sodium carbonate. My acetic acid, I get 0.100 moles of acetic acid. My sodium carbonate's a 1-to-1 ratio. This means I have made 0.0162 moles of CO2. My acetic acid will make 0.05 moles of CO2. Which one is my limiting reagent?
Sodium carbonate?
Sodium carbonate, it's the smaller one. So when I plug my values into my ideal gas law, I'm going to use the amount of moles I got from my sodium carbonate. To predict the volume, I'm going to take the moles predicted from my limiting reagent, multiply that by my R, or my rate constant. That gets multiplied by my temperature. That gets divided by 1 atmosphere. I predict this out. This means I should get 0.396 liters or 396 milliliters. Are you understanding where this number came from? And are you understanding that because it came from stoichiometric results, it's the amount we should get? Anybody confused at this point? All right, now what we're going to do, we're going to take the 1.74 grams of sodium carbonate. We're going to put it into a balloon. We're going to tie that balloon to the very top of a flask in which we've already added 100 milliliters of 1 molar acetic acid. Then we're going to tip the balloon over. We're going to get all that powder down. The sodium carbonate is going to hit the acetic acid. It's going to make bubbles. It's going to make more and more bubbles. We're making lots and lots of CO2. The balloon is starting to get bigger. Now, after the balloon gets bigger, after it's gotten no bigger, we're going to take a pair of calipers and we are going to measure the diameter. Now, I gotta change out of this to the other screen for a second because I don't have access to I don't have access to this diagram. Now, if I am going to actually measure the amount in our balloon and the amount that's above our liquid, I have to account for several things. This is an example of what's happening. Note, there's a liquid here. There's an area above the flask, above the liquid. The volume above the flask, or above the liquid and still in the flask, is 170 centimeters cubed. This little bit, the neck of the balloon, that's 10 centimeters cubed. And we can get the volume of a balloon. We can get the volume of a balloon by taking pi times the diameter cubed divided by 6. So we're taking calipers, measuring the diameter of the balloon. We're plugging the diameter into pi d cubed over 6, and that will be our volume of the balloon. We have to add 10 to that. To that, we have to add 170 to get the full volume of the gas. So I use 4/3 pi r cubed. It's the same formula, only I'm using the radius, he's using the diameter. Just go ahead and use the diameter formula. So if my volume of my balloon is 4/3 pi r cubed, I need to find out what that volume is. If my diameter is 7.596, half of that's the radius, which means it's 3.798. I take 4/3 times pi, 3.14, times my radius cubed. This gives me the volume of just a balloon. To that, I have to add the volume in the airspace above the liquid in the flask and the neck of the balloon. I end up with 409. That's compared with the 496 we predicted. All right. Now, there are some inherent errors in this experiment. Things that guarantee you will not get the right answer. We're going to do a group discussion of those right now. What possibly could be wrong with this experiment? All right, let me ask another question. When we did the actual ideal gas law, did we measure the pressure?
Is the screen up? I don't see it.
There is no screen, Armethea. We're just in a discussion right now. One of the questions you're going to be asked is what possible errors could happen in this experiment to cause you to have a bad result. There are some inherent problems with this experiment. Can anybody, this is a group discussion, guys. This question does exist. If you don't want to deal with it, give me the 15 points. I'll stop right now. What possibly could be going wrong? And I come back. When we use the ideal gas law to make our prediction, Did we actually measure the pressure or did we measure the temperature?
No.
Could they be different?
Yes.
Yes.
Two errors right there. Now, again, we discussed this when we first started. We get these cheap ass Walgreens balloons. Are the shape of the balloons going to be spherical?
No.
Yet, what did we use to make our experimental determination of the volume of the balloon? What did we use?
Volume of
that?
a sphere?
Was it a sphere?
No, it was not.
Is there anything else that could have happened in this experiment? There's a 10 out there, guys.
Shake it up all the way so that it didn't react fully.
Absolutely great. Good one, Allie. If you don't shake up all of the bicarbonate, how can you be sure you've gotten 100% of the reaction? All right. The way they tell you to do this experiment, they tell you to weigh the balloon, then put the powder in the balloon, weigh it again, then put it on top of the flask. What are the chances of all the powder getting from the balloon into the flask?
Not very good. I mean, yeah, no.
Okay, guys, those are available for you. I got nothing else. Are you okay with this? Does this make sense to you?
Makes sense to me.
Same here.
Unless you got something else, guys. I've been on here about an hour, so I'm happy to stay and get you on the right path if you're not understanding what's going on. Other than that, guys, I will see you next week then.
All right. Good night.
Good night. See you next week.
Have a good night.
Night. Have a nice weekend.
Take care.
I just had one question about, I feel like I overthink some of these problems with the significant figures of, that's my biggest thing.
Okay, Allie, I've seen. That is definitely, I mean, I looked at your solution thing. If you go back and look at your solution thing, I see 2 points being taken off left and right because of the fact you don't have your sig figs right.
Yeah.
It's not going to be such a problem in this one because you have a range of the weight that you're supposed to pick out. Okay. So you shouldn't have that much of a problem. Where do you have problems with the significant figures? Have you been able to identify where your problem's at?
Not really, because I feel like, with the addition rules is one thing, and then the multiplication, and it's like I'm keeping the least significant figure. And I think when I'm working through the problems, I'm wondering if I should be.
Two separate rules.
Yeah.
You got to bifurcate your mind. You got to say, okay, this is the operation addition, subtraction. Addition, subtraction, that's where you go to the number that goes to the right, the smallest amount. So if you have something, you have 0.001 and you're subtracting out 0.0009. Okay? The first one goes out 3 places. The bottom one goes out 4. So literally speaking, in that particular example, your answer would be 0. 0.001 minus 0.0009. If you do the actual subtraction, you get 0.0001, but the original 0.001 only allows you to go 3 places past the decimal, right? So you look places past the decimal, look to the right, that's a 1, you can't round up. So for all intents and purposes, that's 0. When you're
Okay.
adding and subtracting, you look at how many places the number goes to the right. And that the one that goes to the right, the shortest amount, that will tell you how many significant figures you have.
Okay.
Now, multiplication division is a lot easier. All you got to do is count the number of significant figures in both numbers. Whichever one has the smallest amount, that is the one that dictates how many significant figures your answer will have. If you
Mhm.
multiply 25 by, and I don't have my calculator with me.
If we're doing like multi-step problems, do you
Okay,
just keep it for your least in the problem? Like,
do you want to know the real way, or do you want to know if you're struggling with significant figures, what I would tell you to do?
that way.
All right. What I would do is I would go each step. And mathematics has a specific order in which they do steps. Everything in parentheses gets done before everything outside the parentheses. So if you have 6.0 times 3.55 plus 0.45. Okay, what was the first number I mentioned?
6.0.
6.0, okay? Now,
Mhm.
my 3.45, the operation inside, my 3.45 plus 0.45 dictates that my answer should be out 2 places past the decimal. Does that make sense?
Mhm.
So my real answer should be 4.00 inside the parentheses,
Right.
but I'm multiplying that by 6.0. I multiply 6.0 that has 2 significant figures by 4.00 that has 3. My final answer should have 2. So my final correct answer is 24.
Okay.
Is this kind of making sense, Allie?
Yeah. I think I just mixed things up with the addition subtraction, which was throwing me off in the last, like I knew what the answer was, and then I was just overthinking filling it out.
You know, to be honest with you,
Yeah.
I feel good that this is the biggest problem you have in chemistry right now. And you should feel good about that too.
I do, but then I get frustrated a little bit because I'm like, I know it, but there's all these, yeah. I knew filling it out the last go around. I'm like, what I'm going to miss on these is it's
same
the
thing.
significant, yeah. But it just, yeah, something I'll have to keep working on. We didn't go over it in our lecture, so it just is like,
You didn't go over it in your lecture?
well, he doesn't use significant figures. It's not a thing. So it's always just something
Well,
like,
to be honest with you, I'm glad I harped so much on them,
yeah,
because if I wouldn't have harped so much on them, then you would have gotten completely to Chem 1 and been blindsided.
yeah,
So there is at least that for you.
yeah.
I think we've had this conversation before, and I think I've told you before, it's unconscionable.
Mm-hmm.
But he's decided that he wants to see that you know these other things. So I'm going to concentrate on whether you know these other things, and significant figures, I don't need them so much.
Yeah.
Eventually, that would end up biting you in the butt.
Yeah. But I appreciate you taking a couple extra minutes because it does
No problem.
clear it up a little bit for me.
1 second, okay? Okay, yes. And I want, this doesn't matter. Okay, Ally, we're going to take some time to do this right now, okay?
Okay.
No, this is not what I want. I want, okay. Now this should, hopefully this should work. Okay. All right. Do you know the basic rules behind them?
Yes.
All right. So any non-zero is a significant digit.
Mm-hmm.
3 classes of zeros. Leading zeros. If it's a 0 to the left of any number, not significant. If it's a 0 between digits, it is significant. If it is trailing zeros, that's an iffy position. Trailing zeros are only significant if the number has a decimal point. Decimal point anywhere within the number, all trailing zeros are significant. No
Mhm.
decimal point, no significance to the zeros. All right, we good with that?
Yes.
Exact numbers have an infinite number of significant figures. 1 inch is equal to 2.54 centimeters exactly. All right, it's an exact comparison. So literally speaking, if I was going to consider it, there are zeros to the right of this 4, correct?
Yes.
And don't they extend out to infinity?
Yes.
So if I have an exact number, you're going to have zeros that extend out to infinity. The exact number will always have more significant figures than whatever it's compared to.
Okay.
So that's why you don't determine significant figures by using any
Factor.
exact
Okay.
numbers.
Okay.
Counting numbers are exact numbers. All right. For multiplication and division, the number of significant figures in the result has the same number as the measurement with the smallest number of significant figures. I have, where'd that? Did your slideshow go crazy?
No, I still see it.
Mine did. And I don't know why it did that, because my share screen is screwed. You're still seeing the PowerPoint, I take it.
Yes.
All right, good. All right. So I've got something with 4 sig figs, something with 2. Always do the math out roughly. Then after you get your final number, you're going to go from left to the right. I have 2 sig figs. So this one and this one count. The 3 is the last one I can count. I look to the right. That number is greater than 5. I round it up to 7.4.
Mm-hmm.
We have a multiple thing here. Okay. What you're really supposed to do, Allie, is you're supposed to kind of like in your head, figure out how many significant figures your final answer should have.
Mm-hmm.
Then you use the rough numbers to come up with a rough answer. Then you truncate it to the correct amount of significant figures. All right. How many sig figs is this number?
1, 2, 3, 4, 5. And
This
then
number
3,
divided by how many numbers?
4.
So if I'm taking 5 multiplying by 3 sig figs dividing by 4, How many significant figures should my final answer have?
3.
Okay. I got 4.5 times how many sig figs is this?
3.
I've got 2 times 3. Final answer is 2.
Okay.
If I'm doing addition and subtraction, what I have to look at is how far to the right the
Mhm.
units go. In this case, my top number goes 3 places past the decimal. My bottom one only goes 2 places. So the best way to do this is to draw your numbers real neatly, then find the number that goes to the right the least and draw a vertical line just to the right of that.
Mhm.
If I did that, my vertical line would be right at this 7. I then look to the right. That number's 5 or greater. I round it up, 31.28. You can't be fooled by something that doesn't have a decimal place. You got to just realize this goes out. How accurate is this?
To the 5.
To the 5, which is the tens place, correct?
Mhm. Yes.
To that, you're adding something that goes out to the 0.1 place. This one only goes out to the tens place. This goes out to the 10th place. So my answer can only go out to the tens place. Why is that small? Well, it's because I did that. I'm sorry, I'm trying to do this on the fly. Okay.
Okay.
All right. You have this number added to this number. I'm going to go through and I'm going to add them together. I got 1, 3, 4, 3, 4.576. What do I report that number out as?
Well, we can only go to the tens, hundreds, thousandths place. So 1, 2, 4. So 1,340.
Okay. This one, the last significant figure occurs in the hundreds place, right?
Yes.
All right. This one goes out to the thousandths place.
Mhm.
So you saw right away that this is the last significant figure you have to deal with, correct?
Right.
So it is in the hundreds place. That's the furthest this place goes to the right, is a hundreds place. So therefore, my answer can only go to the hundreds place. So that's the one that I then have to decide whether I'm going to round up or round down. I look to the right. Am I rounding it up or down?
Down.
That is your answer. Okay?
Mhm.
Okay, Ally?
So I would do my parentheses first, and I can only go to the tenths place.
You're going to have to do them. If you have a calculator, you're going to have to do that subtraction.
Yeah, I do. So 37.3. And then 3 times my 14.64. So
Give me the rough, tell me what the rough number is.
the rough is 546.072.
Okay, so how many significant figures are you going to limit that to?
3 for my 37.3, so 546. Okay.
You feeling a little better about this then?
I'm feeling a lot better about it now.
No
Like
problem.
all the
Have-
steps.
Ultimately, Ally, this 20 minutes or so we spent,
Yeah.
this is more satisfying to me than sitting in that classroom droning on with half the class that doesn't want to be there. Okay, does that make sense?
Yeah.
This is really more satisfying because any teacher that has a student that really wants to learn something, if they don't go out of their way to help that student, then they're a lost cause as a teacher. So I'm happy to do it.
I appreciate it.
I'm happy to stay here and do more if you want more.
I think I got it. That's good.
Okay.
I'm wearing down myself. I got the second dose yesterday, so today's been a little rough for me, but
My wife reacted, I didn't.
oh really?
Yeah, so
Yeah.
she got chills and was really just feeling achy.
What I
The
got.
day after she got the shot.
Yeah.
Pfizer, Moderna, or Johnson and Johnson.
The Pfizer.
Good
But
for you.
chills all day. So the body aches. That's been hoping tomorrow it's gone, but
Well, hopefully you don't have to work and hopefully you can just relax all day.
I did work today. I did take tomorrow off, but yeah, I'll be taking it easy.
Good, good.
Thank you for
No,
taking
if you need anything ever, Ellie, just give me a holler, all right?
I
That's what
appreciate it.
I do this more for this portion of it rather than the money.
Yeah.
Okay. So you take care and I will see you again next week then. Okay.
Yep. I'll see you on the Zooms.
Did we talk about whether or not you were taking Chem 1 in the summer?
I'm gonna do the college algebra. I'm just gonna do that one, and then hopefully fall or like the next round, whatever, I'll get into Chem 1.
Keep my number, Allie.
Okay. I hope you're teaching it. And
I don't know. I don't know what I'll be teaching. As a matter of fact, he intimated today that he's got the schedule for the fall going. So I have no idea what he's going to give me. He might
Okay.
very well give me Chem 1.
Well, I'll have my fingers crossed then.
No, good enough. You take care
All
of
right.
yourself and I will talk to you next week then. All right.
Okay.
All right.
See you.
Bye.
Thank you.